Our first input refers to the wheel load or wheel configuration. We can choose between single wheel and dual wheel. In our example, we'll use the single wheel configuration. We define an axle load of 80 kilonewton, which is equivalent to 8 tons. The next input is the wheel width. We'll define 30 centimeter wheel width. By entering that number, we directly see the resulting stress underneath of approximately 565.9 kilopascal. Next, we are defining the design requirements, which are referring to the allowable rut depth, which we will define with 50 millimeters, and the number of total axle passes. For our example, we will define 200,000 axle passes. You can see a tick box at the bottom of the design requirements input window. If we tick this box here, we have the option to define the effect of wheel wandering. Wheel wandering refers to the vehicle's wheels not maintaining a straight path. With the effect of wheel wandering, the load below the wheel spreads out over a wider area of the road, which is reducing localized stress in the rut zone that experiences the highest number of axle passes. If we consider the wheel wandering effect, this leads to a more optimized design. In our example, we will not consider the wheel. Next, we are defining material properties. The first property refers to the subgrade material. If we click this box, then we have a selection of different soil types. And this is a way to define the subgrade strength in terms of a CBR value or an EV2. So if we don't have a soil investigation report, which clearly states the CBR value, but we know what type of subgrade soil we have in our project, we can define this, and then the software will propose a subgrade CBR. Like for peat, it proposes 1%. We can also correlate that to EV2 and use the value which is relevant for the area where our project is located. But in our design calculation example, we'll go with the CBR value. If we have at a later stage information which will give us a slightly different value, we can tick the box below and override this value of 1%. But in our example, we'll leave it at 1%. Also, the correlated resilient modulus can be overwritten if we tick the box, and then we can change that value. The next input refers to the base course material. Also, if we don't know exactly what it is, we can select from a given list of materials, which starts with sands, gravelly sands, and crushed stones of different grading. In our example, we'll choose a 0 to 63 crushed stone material. The next input is defining our chosen reinforcement product. Again, there is a menu from different products we can choose from, and we will select for our example a CombiGrid 3030Q1 GRK4C. So it's a geogrid with 30 kilonewton biaxial strength and a geotextile separator. The next input is referring to reliability factors. In total, we have 5 factors that influence the structural performance of the road. The first one refers to the long-term bearing capacity of the foundation. So the long-term bearing capacity depends on drainage conditions at subgrade level. If we open this up, then we can choose between well-drained conditions, partially saturated, or high risk of permanent saturation. We'll choose a well-drained subgrade. The next reliability factor refers to the base course installation and compaction. So the quality of compaction, of course, influences the long-term performance of the road. We can choose between 100% proctor density up to less than 98%. So we'll take the highest degree of compaction with 100%. The next reliability factor refers to the quality of the base course material. So this refers to the grading of the material, and we will select a well-graded crushed stone with a D60 versus D10 greater than 5 millimeters. Then the second last reliability factor refers to the maintenance level. So if we open this up, we have again 3 choices. The first one is referring to a continuous maintenance approach. This means that ruts will be filled, leveled, and compacted. The second one means we have only a temporary maintenance, only extreme ruts will be filled, leveled and compacted. And the third option is a limited maintenance approach where ruts will be leveled with no additional fill material. We'll go for the first option of a continuous maintenance approach. And the last reliability factor is referring to the performance. So this refers to the acceptability of the rut depth. The first option defines an exceedance of the maximum allowable rut as acceptable. The second option means limited exceedance of maximum rut is acceptable. And the last one says maximum allowable rut depth must not be exceeded. We'll go for that one. So the defined value of 50 millimeter, which we have defined at the top, will not be exceeded in our design calculation. With this, we have finished the input procedure and we can click on the continue button, which activates the calculation process. On the next page, the summary of the calculation results are displayed. At the top of this page, the thickness of the reinforced solution is shown. Under the given conditions that we have defined, the calculation is proposing 40 centimeter of a crushed stone on top of a Combigate 3030 Q1 over a subgrade with a CBR of 1%. The unreinforced section uses 79 centimeter to reach the same condition, meaning to not exceed 50 millimeter of rut depth. This difference equals 49% of material saving by using one layer of a Combigate 3030 Q1. At the bottom of this page, we can see the definition of the stone material, the specification of the grading, the Combigate type, and the required thickness for reinforced and unreinforced. If we click on the continue button, we have the possibility to also print a design report. By clicking on this button, a PDF report is generated, which will be saved to the download file on your computer. The design report is summarizing all defined parameters of your project, which starts with your axle and wheel configurations, the number of axle passes, the allowable rut depth, the chosen reinforcement, and on the last page it shows the two typical cross sections of the calculated base courses, showing the reinforced at the top and the unreinforced, and a saving of 39 centimeter of unbound aggregate using one layer of Combigate 3030 Q1.